太大，太高了，这样子。所以那个被人家调过。对对对，他最近这2天，好几个老师反映。
喂 ，OK。是那个 gain 是哪一个？啊 ，OK。好，谢谢。Okay, so we consider find the general solution of the wave equation. All right, and the region we consider is actually southern region. Such that so which is the okay. So the domain, okay, the region. Let me just write down the region here. All right, so a general solution can be obtained immediately by transforming the xt coordinate system to a suitable VW coordinate system. As follows. V is equal to x plus ct, and the W is x minus ct. Okay. So you see this, the new coordinate is a linear transformation of the old coordinates. Okay. As you can see that VW xt here is 1 c minus c. Okay, and it's immutable because the determinants of the of the transformation matrix 6 invertible, because the determinant is minus 2c, and the c is the velocity, so usually this c x naught 0. Okay. All right. So the inverse. So the inverse coordinate transformation x here, the x is equal to q v plus w, and the t is 2c v minus w. Okay. So that we have the coordinate transformation. Okay. Okay. All right, and we know that the first order partial derivative, first of all, because v and the v here as a function, okay, it's a linear function of x and t, so this is E1, and vt is equal to c. The partial derivative of the w coordinate is 1, and the wt is minus c. Okay, this is about the first order partial derivatives. And how about the second order, because we will use that. So the second order, this is 0, and vtt is equal to 0, and wxx equal to 0, wtt is equal to 0. Okay. All right, now, so we define the U tilde VW because of the coordinate transformation, so that the x from here, x is a function of the new coordinate, and t is also a function of the new coordinate. Okay, so we do so this is the, after the coordinate transformation, that the u function becomes to the u tilde as a function of new coordinate, v and w. So any questions about this? Okay. Okay, so this is differentiation. Okay, and then we have, so to obtain u from u tilde, all right, then we know that u tilde, and we do so v is xt and the wxt. Okay, so we have all these things together. Now the original wave equation is coordinate in the coordinate system, xt coordinate system. We want to find the corresponding wave equation in the new coordinate system. VW, okay, so that so we first of all ut, and so we see that the first order partial derivative, all right, and for here, so we use the chain rule. We use chain rule here. First of all, this is u tilde V, okay, and Vt plus U tilde W and Wt here. Okay, this is by chain rule. Any questions? Okay. If you have any questions, just let me know. Okay. Okay, and so we have U, V height, and no, tilde, not height. Sorry, U tilde. Now, Vt is C, right? And Wt is minus C. So we have C of U tilde. And the first, yeah, okay? So that we can, the first order positive derivative of U with respect to T is equal to this expression corresponding to the first order derivative, positive of U tilde with respect to V. And here, this is the first order partial derivative of U tilde with respect to W. Okay. And the UTT again. So now we have C constant. All right, and for this one, again, by the chain rule, so we have U tilde, V, and Vt, okay, because we take the positive derivative with respect to T again, and plus U tilde, Vw, and Wt, okay. Minus here is U tilde W Vt minus U tilde Wt. Okay. Again, once again by the chain rule. Okay, and as we see. Vt is C and W sub T is minus C. Okay, so we have so this is minus C. So we have C square again. Every time we have, and here is U tilde V. So this is the second order positive derivative of U tilde minus 2. Okay, if you like, you can have U tilde VW minus U tilde W here plus U tilde W. Okay, so we have these terms. Now Ux here. So Ux, you have U tilde V, Vx plus U tilde W, Wx here. Now, Vx, this is 1, and Wx is 1. So we have here U tilde sub V plus U tilde sub W. Okay, and finally, this is second order partial derivative with respect to x. Okay, and this is U tilde Vx plus u tilde vw wx plus u tilde w vx plus u tilde w and wx here. And again, v sub x is 1, w sub x is 1. So we have for here u vv tilde plus u tilde vw plus u tilde w plus u w tilde. Okay, so we have that. And the wave equation involves these two second order partial derivatives. Okay, so now we know u tt is equal to c square u xx. Okay, and utt is the c square of uv tilde minus u tilde vw minus u tilde v plus u tilde w equal to 2 uv tilde plus u. C square. This C square here, sorry. Alright, so we eliminate them. Okay. So we have that removed there. So we have u vw tilde plus equal to 0. Okay. And so this is equal to u, by assuming that the mixed second order partial derivative equal. Okay, so we assume that. And that it can be for sure when some continuity property holds, right? But now we just write it then. So the wave equation. So this is the wave equation in xt coordinate system. And here is the wave equation, the PDE in the VW coordinate system. Okay. The coordinate system there. Okay. And we take a look. The transformation here, the transformation, as we see that we have, so that the region, we have the R is in there, and so that so, Okay, so we have now and a general solution of is here. Okay, equals to C5 plus CW. Right. Okay, so we just do it. All right. So first of all, when we do the integration, now so we have U tilde W XD by V here. Oh, let me see. So this this is 0. Okay, so which implies that constant. So this is per C. Per C W. Is that correct? W, yes. So this function with respect to okay. All right. So this is I say this is equal to prong. Okay. Prong is not a good thing. Let's say alpha function. Okay. Maybe I used. And then when we do the integration again, so the U tilde VW becomes to plus C of V here. Okay. And this is, we define this is as per C of W plus 5V. Okay. So a general solution of becomes to 5 plus per C. Okay. where phi and per c are arbitrary functions defined on R. Okay. Defined on R there. Such that and there are some requirements. For example, we want the U tilde to be to have continuous. For example, we have continuous mix. So we have this identity. And for example, continuously that's fine at this moment, okay? Okay. So with let me that is the coordinate transformation and CT, okay. That UXT is the U tilde, VXT and WXT. So this is become to phi x plus CT plus C x minus CT. All right. So phi and C can be arbitrary functions, but so I have to remark some properties of phi and per C will be imposed. Now, to make sure the differentiability all right, of U tilde. Okay. Okay. For example, in this equation, in here we need that they have a second order partial derivative, for example. Okay. And if we require that the second order partial derivative is continuous, then we need more information, more property about the phi and the per C. Okay, so this you need to impose some additional properties. Okay, but at this moment, we just write down the general solution like here. Okay, so that right, so we have this solution, general solution, right? So which is known as the numbered solution of the wave equation. Right. And for our purpose, so here we assume that both phi and psi are twice differentiable. Okay. This is a list that they are twice differentiable. And maybe it's possible that we may need to assume that the second derivative of phi and psi are continuous, maybe, right? If needed. Yeah, okay, if needed. Now assume that the following initial condition are given. So we want u x0 is equal to, we say, f star of x, and the initial velocity is g star x, right? So with that, okay, for two functions, f star and g star defined on the whole real line. Okay, now since u t, okay, so the first partial derivative, okay, is equal to c times phi prime, okay, x plus ct minus c plus c prime x minus ct. Okay. Right, so the two initial condition okay, implies, so this imply that right, so we write down u x0 is equal to so when t is 0, so this is phi of x plus psi of x, okay, is equal to f star x, and ut x0 is equal to c, alright, and phi prime x minus c plus c prime x is equal to g star x. Okay, and this one by integration, so we have that phi x minus psi x is 1 over c, and we will do integration, right, take the x0 here, g star of s ds plus phi of x0 minus c of x, and c of x0 here. So this is by integration. Okay. All right, and we have two equations together. All right, so that's the phi, okay, is 1/2 of f star x plus 1 divided by 2c x0 to x g star s ds plus 1/2 of phi x0 minus c of x0, okay, and c of x is equal to half of f star of x plus 1 over minus 2c minus half okay. So from the two initial conditions, yeah, because the general solution consists of depends on two functions defined on the real line. So two functions is phi and c. Okay, right. And so to determine these two, so you can see that this is the waveform propagate to the left. So the direction the wave will propagate to the left real axis. Okay, so it's to the negative direction. Okay, as t goes up. But this one is the wave go right. Okay, let's go right. Right, because as t go up, right, and the axis should be increased to remain the same wavefront. Okay, so this is the wave. So this. Right, so this is the wave traveling to left, and the wave traveling to right. Right, so that's one is go this way, the other is go this way. Okay, right, and so we have to know the wave shape, the phi. So phi is the wave shape traveling to the left, and the c of x is the wave shape traveling to the right. So to find the solution, this is general solution, right? But to find a unique solution, you need two conditions, okay? And for here, we fulfill two initial conditions, all right? So this is the initial position, okay? And this is the initial velocity, okay? At every point, every location, okay? Location, and all right. So from there, we actually solve these two wave shapes, okay? These two wave shapes in terms of f star and the g star. All right. So the solution of the wave equation, okay, satisfying the two initial condition in the above is here, is the u of xt equal to half of f star x minus ct plus f star x plus ct plus 1 over 2c and x plus ct, x minus ct, g star x and dx. Okay, so if you add them together, so this is the Lambert's solution, right? So now we have that. Okay, and these two constants cancelled because when you add them together, they just cancelled. Okay, so you have this one, and okay, and this is good for all x in R and t greater than or equal to 0. Because we consider that the x is in the whole real line. Okay, so the wave will traveling wherever, right? We're traveling to left, to right. Okay. Okay. So basically, there's no boundaries. That's why we can only impose initial conditions, no boundary conditions needed here. But suppose, furthermore, right? Suppose that two boundary conditions are imposed. Okay, at the point x equal to 0 and the point x equal to L, right? So that we need that equal to 0 and u LT is 0 for all t greater than or equal to 0. Suppose that. Right, so we impose this condition. Then we must have here that is 0, right? And we put x equal to 0, so that is 1/2, and f star minus ct plus f star ct plus 1 over 2c and ct minus ct g star x ds. So, okay, so this is 0. And we put L into there, so that 0 is 1/2 f star L minus ct plus f star L plus ct here plus 1 over 2c and L plus ct, L minus ct, and g star s ds. Okay, so this must be true for all t greater than 0. So you should have these two equations. Okay, so we ask for that at the position, which means that at the position 0, the two traveling waves will cancel each other always. Okay? Will cancel each other. And also at x equal to L, the two waves also cancel each other. Okay? So that you have a 0 here. Okay? Because this is always true for all t, right? So at any time, starting from 0, that the two waves will cancel each other. So basically here, so you can see if you look at the original the numbers solution, so you see that 0 is u t, which means that phi ct plus c minus ct is 0. Okay? Must be 0. And 0 phi L plus ct plus c L minus ct must be 0. So they have to cancel each other for all t. Okay, if we imposing if we impose the two boundary conditions at x equals 0 and xl, you can see that they should these two waves should cancel when they travel. All right. So this one travel to the left, this is traveling to the right, so they should cancel always. Okay. Okay. Now, in the previous section, okay, the initial condition all right, are specified only on the interval 0L. Okay, so we specify the initial equal to f of x and ut equal to g of x for all x in 0L. With where f0 equal to fl equal to 0 and g0 equal to gl equal to 0. Okay, as required by the boundary condition. Okay? At x equal to 0 and at x equal to L. Alright? Now, so we specify only in this interval. Okay? So now we may regard okay, f and g to be in the half range of odd periodic function f star and g star respectively. Okay. Okay, so now we may specify the two initial conditions, okay, here, such that because this is the is a function defined on the whole real line. Okay, and so we regard f star is a periodic function, and f star and g star are the periodic function. Okay, so f star is equal to f of x when x is in 0 and L, and minus f of minus x when x is in minus L to, okay, and f star x plus 2L equal to f star x for all x. Okay, so f star is a periodic function, okay, and it is odd because we define it in this way. Okay. And the G star is also an odd periodic function. Okay, so we use these two functions. Okay. All right. So now with such, so when we define the f star and the g star, okay, by using the two initial conditions given in half range in from 0 to L, with this, right, required by the boundary conditions, we have that. Now, then we can check that these two conditions are satisfied, right? So now, okay, so now since f star x and g star x is they are the functions on R. So we see half of f star minus ct plus f star ct. Okay, so we check that f minus ct, f star ct. Okay, we see that. So this is 1/2. And because it's odd function, so this is equal to minus f star ct plus f star ct. So this is 0. Okay, and we look at ct minus ct g star x ds, also 0. Okay, because g star is an odd function. So you see that this is 0 and this is 0. So the sum is 0. Okay. But for here, we justified. So this is implies that 0 is half of which is needed. Okay, which relevant to the which justifies the boundary condition that u of 0t is equal to 0 for all t. Okay, so this justifies the boundary condition. Okay, and also since f star L minus ct, which is equal to f star L minus ct minus 2L, because f star is a periodic function, right? Here f star is a periodic function. Okay, with a period 2L. Okay, so we have 2L. Okay, so we have that. And so this is f star minus L plus ct. Okay? Now, because f star is odd function, so this is minus L plus ct. Alright, so the half of f star L minus ct plus f star L plus ct becomes to 0. Okay, so now this term here is 0. So now we check this one. Alright, and since G G star, okay, and T plus L, since G star T plus L, so we promote that, is also okay, maybe I will write here G star minus T, okay, plus L, okay, which is equal to G star minus T minus L minus 2L. Okay, so again, this is G star is a periodic function with a period 2L. Okay, so minus L, and this is G star minus T minus L. Okay, all right, and we take this way, And because G star is odd function, so this is minus G star minus T, G star T plus L. Right, so G star minus T plus L equal to minus G star T plus L. Alright, so this means that G star, so if we define HT to be G star T plus L, so this function is an odd function. Of T in R. Okay. Right, so we define a new function which is G star of T plus L. Okay, now HT is an odd function. So now CT and L minus CT and G star S and DS. Okay, now this is equal to CT minus CT and G star S plus L ds. Okay, so by we are okay. We might use dw z dz. Here S is defined to be C plus L. Okay, so we do the change of value of the S is equal to Z plus L. Okay, and so that the integration limit becomes to minus T to CT here. And then this is equal to CT minus CT and the H of Z and dz. Okay, but H of Z is odd, so this is 0. Okay, so that this integral is also 0. Okay, so together, this is implies that 0 is equal to half of F star L minus CT plus F star L plus CT. Okay, and plus 1 over 2C integration L plus CT L minus CT G star S ds. So this is 0. Okay, so this which justify. So this justifies the boundary condition. That ULT is 0 for all t greater than equal to 0. Okay, so indeed, we have that one. So the solution, the lambda solution here, this is solution, would be the solution of our wave equation with the 2 initial conditions and 2 boundary conditions. Okay, and this solution have F star and G star defined by defined from the f of x and gx here. Okay, so F star and G star, they are odd periodic functions. Okay, so they are odd periodic functions. Okay, so F star and G star. Okay. So this solution is true for all x in R. Then and also it satisfies initial condition and boundary conditions in the finite interval from 0 to L. Okay. So of course it's still valid for x in 0 to L. Okay, in 0 to L. There. Okay. Okay. But when you write down, you have to use the F star. Okay, you have to use the F star because X star they actually define in the whole real line. Okay, remember the F and the G is defined only for X in between 0 and L. Okay, so you can't say, oh, this is F. No, why? Why? Because if X is 0 and T is positive, then this argument is negative. Okay, and for a negative argument, you see the F function is not defined. F function only defined in this interval. Okay, it's only the extension F star and G star from F and G to be the periodic function. So the F star and G star are functions defined on the whole real line. Okay, so the waveform itself, the wave, okay, the wave, to satisfy the two initial conditions and two boundary conditions, two initial conditions. Yeah, okay. So this is the boundary condition, this is initial conditions. Corresponding to the wave function. Okay. Right. So there are two components here. Right. So this is, of course, that F star has two traveling wave, and also the third part here. This contributed from the initial velocity. Okay. And again, G star is still odd periodic function. Okay, defined on the whole real line. Okay, any questions? So even though we find the general solution, right, by the Lambert method, so but we see that we can, from the general solution, we can obtain the unique solution we have in the previous section under the two boundary conditions and two initial conditions. Okay, for the position, x is from 0 to L, but for the time, starting from 0 to infinity. Okay, so this is the region, we have restricted region there. Okay, and the numbered method deal with our wave equation, and the region is actually the whole real line, and the term is from 0 to infinity. So the region is much bigger there. Okay, so we can still find general solutions, and from these general solutions, by suitably select the proper initial conditions there. Okay, because the region covers whole real lines, so that we don't have the boundary conditions in the general solution. But two initial conditions will be required to find these two traveling wave shape, the phi function and the perceived function, as we know here. Okay, so that we actually find out the phi function and the perceived functions in terms of the f star and the g star. Okay, so that they are particular solution we have, and from that we can actually recover our solution in the previous section. Okay, if we impose boundary condition at 2 points, x equals 0 and equal to L. All right, and the two initial conditions specify only for this range. Okay, and then the solution is obtained through the numbered solutions by given f star and g star in terms of this construction. So f star and g star becomes to R the periodic function. Any questions? Okay, so if no questions, okay. So let's take a break up to 2:45. Okay. Okay, now from our previous discussion, we know coordinate transformation and is very successful, right? At least for the wave equation. So we are able to find general solutions. And I know you have learned some exercise that in the previous recommended exercise to know that similar coordinate transformation can lead you to find a general solution for PDE. Okay. And so the result is that, especially in the mathematical history, people think about can we extend the method of coordinate transformation, okay, to other more general PDE. Okay, so this is the so the following discussion is about the extension of this idea. And especially will apply to so we will give a special subsection classification of general second order semi-linear PDE, okay, with here with two variables. So we restrict ourselves to functions like in the one-dimensional wave equation there are two variables. One is x, one is a spatial variable x, the other is time variable t. Right. So we consider a general second order semi-linear PDE with two variables. Okay, so we have A of xt and utt plus b of xt and uxt plus c of xt and uxx equal to f of xt ut and ux. Okay. Right, and it's semi-linear because that we have only linear terms for the second order partial derivatives. That is 3. Okay, and the coefficients depend only on the two independent variables x and t, not on ut, ux. Okay, and but this function may be highly nonlinear with u sub t, u sub x, so they can be arbitrary. Okay, so this is called the semi-linear PDE we have here, where the coefficient axt, bxt, and cxt are assumed to be so we assume to be continuously differentiable. Okay, do we own an open subset U xt plane. And at least, so at least one of them is not identical to 0. To 0 on U. Because if all ABC are identical to 0, then we have no second order term that way. So at least one of them is not identical to 0 function on U. Okay, so that is now we want to classify, right? Such a general linear second order semi-linear PDE. Okay, so we say that. So the semi-linear PDE. Okay, in here, so we'll say this is 12.4.1 and 12.4.1 is said to be hyperbolic and parabolic or elliptic. At a point x0, t0 in U. Okay, if the b square x0 t0 minus 4 times a x0 t0 and c x0 t0. Okay, so b square minus 4ac. And this is quite frequently met in quadratic equations. So this one is positive 0 or negative respectively. Okay. We have assumed that ABC, they are continuously differentiable. So ABC will be continuous functions, as we learned from calculus. Differentiability implies continuity. So that this discriminant, b squared minus 4ac, so it's a function of x of t, so that the mass is also a continuous function. Okay, it's continuous functions. So that the value can be positive 0 and negative, right? All right. So if it's 0, right, for on some curve, and it is positive in some it's usually in some open set. Okay, so we can divide the whole plane into either the positive parts, 0 or negative valued parts. Okay, so you have okay, so so that so the same PDE may be hyperbolic at some points and parabolic at other points, even further elliptic in some other points. Okay, so the definition depends on the points here, so that what is the value of this expression. Okay. And the semi-linear PD is said to be hyperbolic parabolic or elliptic. An open subset V of U, okay, if it's hyperbolic, parabolic, or elliptic. Okay, at every point in the open subset V. Okay. And this is very possible, as I have indicated that the function, the B square minus 4AC function is a continuous function. Okay, so that if we want the function to have positive values, then you can see that it's an open set. So it's very easy to find an open subset V of the U, such that the semi-linear PD is hyperbolic, okay, at every point in this open subset, or every point is elliptic, okay, elliptic in B. Okay. So now, you can see the semi-linear PD, second order semi-linear PD, has been classified into three types: hyperbolic, parabolic, or elliptic. Okay? Actually, they are corresponding to, if you still remember, the so-called second order curve you learned in high school. Okay, if you still remember that. Okay, so if you have polynomials of second degree in two variables, so this one describes a curve in the two-dimensional plane. Okay, And the curve can be a hyperbola, can be a parabola, or can be an ellipse. Depends on the quantity, right? The one is we call the discriminant, right? Depends on that. So if this one is positive, then you get hyperbola, okay? And if this is 0, you get parabola. And if the delta is negative, you get an ellipse, right? So that's why we have the similar names here, okay, for the second order semi-linear PDEs, okay. So this is kind of a history where people name the three classes of second order semi-linear PDE, right? Hyperbolic, parabolic, and elliptic. Okay. Anyway, so now our purpose is that we will reduce, okay, a semi-linear PDE to a normal form, okay, in a suitable coordinate system, right? Just like we have done for the wave equation, right? Okay. In the wave equation, we do suitable. We select a suitable new coordinate systems, and it's after the coordinate transformation that we end up simplify the wave equation, right? So that the wave equation is so simple that it's easy to find the general solutions. Okay, and so this is so I just said we follow the same idea. Okay, and we will deal with this is actually a very big class of PDE. Okay, so we want to find suitable coordinate system according to the type of the PDE, right? And but we need a big theorem for analysis. Called the inverse function theorem. Okay, I think maybe you already know this from the second semester of your calculus course. Okay, all right. So assume that the vector function, okay, so it has n components. So each component is a scale function, okay, right? So the FB continuously, right? So it's continuously differentiable mapping from an open subset U of the n-dimensional space into Rn. Okay. So each component is a function of n variables. Okay. variables because so we have n variables and we have n scalar functions, so the vector function is n-dimensional. Okay, so f is a mapping from U to Rn. Okay, because we learned that it is continuously differentiable. So usually the domain is an open set. Okay, now if the Jacobian determinants, alright, so Jacobian determinants so the Jacobian determinants, it's actually, we say JF and A, point A. Okay, so which is the determinants, and we know F1. A, okay, and maybe I stand it up. Okay, so the first term corresponding to the first order partial derivative of f1, and the second row corresponding to first order partial derivative of f2. Okay, and then the last row corresponding to all the first order partial derivative of fn. Okay, right, so this is the determinant of the Jacobian matrix. Okay, so that if we form the matrix, then it's called Jacobian matrix. And the determinants of the Jacobian matrix is called the Jacobian determinants. Okay, so Jacobian determinants, this one is not 0 for some point A in this open set U. Okay, so if we have this property, right, so the Jacobian is there. Then we have inverse function, so that then there are, right, a neighborhood, okay, V of the point A, okay, contained in V. Okay, so we have a neighborhood, okay, and a neighborhood W of f of A, okay, in Rn, such that f the vector function, the mapping, such that f is 1-to-1 in V, and f of v is equal to w. Okay, so now f i.e. f with respect to v to w x 1 to 1 and on 2. Okay, so locally, so we restrict to v, so the mapping when we restrict to v, then v to f with w is 1 to 1 and on 2. So that is invertible. Okay, now the inverse g of f, okay, defined w by g f of x equal to x, right? For all x in v, now the inverse function is also continuously differentiable. Okay, on w. Okay, so if we write the mapping, so this is u, suppose 2, okay, and this is R2, suppose that. Now if you have an A here, such that the Jacobian of f HA is non-zero. Okay, then of course so here is FA, the image of A, okay, here. Now we can find a neighborhood, so a neighborhood V, and a neighborhood W. Okay, so that the restriction, so this is U, right? And the restriction to V, so it's V to W, which is 1 to 1 and on 2. Okay, so locally, right? So locally, the vector function is invertible. Okay, if the Jacobian determinants of the vector function f at A is non-zero, if it's non-zero, then we are able to construct or find a neighborhood of A. So a neighborhood of A is actually just an open subset which contains A, okay, which may be quite small, usually with like a very small open set. Usually it's an open ball, okay, center at A with a diameter which is quite small. What? Oh, in here we say neighborhood is an open neighborhood. Yeah, in here. Okay. But I know in some textbook neighborhood is just that it's a subset which contain whose interior is an open set. So X is inside the interior. The interior always is an open set. Okay. So good question. But in my lecture notes in many other textbooks, neighborhood usually means the open neighborhood. Yeah. Okay. Yeah. So that's a good question. So maybe I will specify that. Where is the neighborhood? Oh, yeah. So just open. Y. And open. So I indicate that. Right. So F we can construct. So F is invertible locally. All right. So we have that. So this is called the inverse function theorem, and the inverse function G, the inverse function G is also continuously differentiable. Okay, also continuously differentiable. Oh, okay. All right. I think I have to stop here. Okay, so we will continue discussion Thursday.